On the 91st floor of Taipei 101, there is a steel sphere the color of burnished gold. It weighs roughly 660 metric tons. It hangs from 8 cables, each thicker than a man's torso, and it sits cradled inside a ring of hydraulic shock absorbers like an enormous pendulum frozen mid-swing. Most of the building's visitors never see it. Most of the people who work in the tower above it have never thought about it. But on a night when a typhoon is pressing against the glass at 200 kilometers per hour, that sphere is moving. Slowly, silently, and with absolute purpose, it is swinging in the opposite direction of the building around it. And the reason it exists tells you something strange and counterintuitive about every tall structure you have ever looked at from the street. The question is this: why would an engineer deliberately design a building to move? Your instinct, and it is a reasonable one, is that a skyscraper should be solid, immovable. That the whole point of pouring tens of thousands of cubic meters of concrete and threading thousands of tons of structural steel through the frame is to make something that does not budge. Rigidity feels like safety. Flexibility feels like a flaw. But that instinct is exactly wrong, and understanding why it is wrong will change the way you look at every tall building you ever see again. By the end of this, you will be able to explain the actual engineering trick to anyone, in about 2 minutes, and they will not believe you at first either. Start with the physics of force. When wind strikes a building, or when an earthquake sends a wave of energy through the ground beneath it, that energy has to go somewhere. It cannot simply disappear. A structure has only 2 choices: it can resist the force rigidly, or it can move with it and dissipate it. Those 2 options sound equivalent. They are not even close to equivalent. Think about what happens when you drag your heel hard against the ground to stop suddenly. If the ground is concrete, the force transfers instantly and completely into your skeleton. If the ground is soft sand, your heel sinks, the energy spreads out over a longer time and a larger area, and your knee feels nothing like the shock it would have felt on concrete. A rigid building is the concrete. A flexible building is the sand. The engineering goal is not to make the force go away. It is to make the force take longer to arrive, and spread it across more of the structure when it does. Rigidity introduces a second and more dangerous problem: resonance. Every structure, regardless of its size, has a natural frequency. This is the rate at which it will tend to oscillate if it is disturbed. A guitar string has 1. A bridge has 1. A skyscraper has 1. The Tacoma Narrows Bridge, which collapsed in 1940 in Washington state, was not destroyed because the wind was unusually strong that day. It was destroyed because the wind was oscillating at almost exactly the bridge's natural frequency, roughly 0.2 Hz. Each small push from the wind arrived just as the bridge was already moving in that direction, and the oscillations built, and the structure tore itself apart. This is resonance. And a perfectly rigid skyscraper, struck by wind gusts or seismic waves that happen to match its natural frequency, faces the same catastrophic amplification. The solution that structural engineers arrived at over decades is to design tall buildings with a carefully calculated degree of flexibility. The Burj Khalifa in Dubai, currently the world's tallest completed building at 828 meters, is designed to sway at its tip by roughly plus or minus 1.5 meters in extreme wind conditions. Not because the engineers could not prevent it. Because preventing it entirely would require a structure so stiff that the forces it absorbed would be enormously larger, and the material costs and the structural weight required to handle those forces would become self-defeating. The Empire State Building, completed in 1931, was designed with enough flexibility that its upper floors can move by roughly 1 meter in strong winds. This was not a compromise. It was the specification. But flexibility alone is only half the answer. A flexible building that is not also damped will swing back and forth, and each swing, if the wind cooperates, can reinforce the next one. This is the resonance problem again, just slower and taller. The engineering solution to this is damping, introducing some mechanism that converts the energy of that oscillation into heat or friction rather than allowing it to keep cycling. And this is where the engineering becomes genuinely beautiful. The most elegant implementation of damping in a tall building is the tuned mass damper. The principle is straightforward, though the engineering required to realize it is not. You take an enormous mass, you suspend it so that it can move independently of the building around it, and you calibrate its natural frequency to match the building's. When the building begins to sway, the mass lags behind due to its own inertia. By the time the mass has reached its peak displacement, the building is already swinging back in the other direction. The mass then pulls against that swing. The two motions partially cancel. The building's oscillation is reduced. Which brings us back to that 660-ton sphere in Taipei 101. Taipei sits in a region of extremely high seismic and typhoon activity. The tower rises 508 meters to the roof and was the world's tallest building when it was completed in 2004. Its designers specified a tuned mass damper of unusual scale, that steel sphere, roughly 5.5 meters in diameter, hanging between the 87th and 92nd floors. The sphere is suspended on those 8 cables and surrounded by hydraulic dampers that further absorb energy as it swings. In a major wind event, it moves by as much as 1 meter in any direction. Engineers who have monitored its performance report that it reduces building sway by somewhere in the range of 30 to 40%. The structure was put to a direct test in 2015, when Typhoon Soudelor, one of the most powerful Pacific typhoons on record that year, struck Taiwan directly. The building swayed. The sphere swung in opposition. The structure performed within its design parameters. Here is the midpoint question worth sitting with: of all the engineering solutions you could imagine for a 508-meter tower in an earthquake zone, which would you least expect the answer to be a giant ball on a rope? Leave your answer in the comments. The actual physics is stranger than the intuition. Now here is the false belief that needs correcting, because it persists even among people who understand buildings reasonably well. The assumption is that a flexible building is one that the engineers could not quite make rigid enough. That sway is a deficiency, an engineering shortcoming that taller and stronger materials will eventually eliminate. The actual engineering position is the opposite. Flexibility is not a consolation prize. It is the primary design tool. The goal, stated plainly, is to allow the building to move just enough that it never accumulates the kind of force that would damage it. The structure is not fighting the wind. It is yielding to the wind, strategically, on its own terms. Other damper configurations make the same point from different angles. The John Hancock Tower in Boston, completed in 1976, suffered a famous series of problems during construction, including window panels that repeatedly fell out. Less discussed is that the building was subsequently fitted with 2 tuned mass dampers, each weighing roughly 300 tons, positioned at opposite ends of the 58th floor. They move in opposition to each other as well as in opposition to the building's sway, providing damping in multiple axes. The result is a building that, in measurable terms, moves less than it would if you had tried to stiffen it by adding mass to the structure directly, because adding structural mass also adds inertia that wind and seismic forces have to act upon. The Petronas Towers in Kuala Lumpur, which stood as the world's tallest buildings from 1998 until 2004, use a different approach, a carefully engineered combination of structural geometry, high-strength concrete with a compressive strength of roughly 80 megapascals in the lower sections, and the inherent damping properties of the concrete itself, which absorbs vibrational energy through internal friction at a microscopic level. The concrete does not simply carry load. It participates in the damping. Here, then, is the actual trick you can explain to someone in 2 minutes. A tall building cannot be made strong enough to simply ignore wind and seismic forces, because those forces scale with the building's rigidity. The stiffer the building, the higher the forces it must withstand, and the cycle becomes unwinnable. Instead, engineers design the building to move by a controlled amount, at a controlled frequency, and then they place inside it a mass calibrated to swing in the opposite direction at the same frequency. The two motions interfere with each other destructively, the way two waves can cancel when their peaks and troughs align in opposition. The energy does not accumulate. It disperses. The building survives not because it refused to move, but because it moved in exactly the right way. The next time you stand in a city and look up at a tower 50 or 60 or 80 stories above you, understand that somewhere inside it, probably near the top where the sway is greatest, there is engineering you will never see doing work you will never feel. A mass hanging in the dark, swinging slowly against the wind, keeping the geometry of the building honest. The machines that move the modern world are stranger than they look. Subscribe, and we will take apart the next giant together.